Our next speaker is Martin Kealy. Martin is with Schirmer Engineering Corporation, and Martin is Director of International Operations. Please welcome Martin Kealy.
Yeah, thank you very much, Bill. It's a great honor to be here to talk to you today about super tall buildings and a new approach to escape. So in summary, I'm going to talk about the code approaches to design currently at the moment, and to look at performance-based design as an alternative, and the importance of communications in a fire condition. A company background is that we are part of Aon Corporation, an insurance company. We've been going a fairly long time, 1939, and one of the first and largest fire protection firm in the USA, with offices in USA, Canada, and here in the UAE. One of the things that we do as part of our contribution to society is that we have 85 professionals serving on 66 technical committees. And we spend 5,300 hours a year investing in the codes. We're also involved in the International Code Council and the NFPA. I'm going to talk about a few projects here very, very briefly. The first one is the Pentominium here in Dubai. That's 120 stories tall. It will be the tallest residential building at that time. We're also working on the Calatrava Spire. I think Dan O'Connor's already touched on that in terms of facades. Also worked on this project in South Korea, the Lotte Tower. And many years ago, we actually designed the fire strategy and designed the sprinkler systems for the Chicago tower there, the Sears Tower. And a project Bill knows very well, it's the Doha Convention Center and Tower. I wanted to go back and discuss how, in particular, the UK codes and the US codes define tall. In the UK, it's 30 meters. In the USA, it's 23 meters. Now, you can see the picture of the firefighters there. That shows a 13.5 meter tall ladder. And you can get aerial ladders of 30 meters. And that's just about the limit of how a firefighter can access a building from the outside. There are other height definitions out there. We found out that working in Korea, that once you go over a certain size and a certain height, you require helicopter access for escape. ASHRAE has a 300-foot stack effect water pressure type threshold. And we know now that once you get to 420 feet, you're required to have 3 stairs under IBC. And that's now adopted and will be in the next edition of the IBC codes. Now, in my paper, I came up with another definition, which was super tall. I just defined that as buildings that were over 100 stories. And simply the only reason I did that is because the current buildings that are around, the tallest buildings now, are around about the 100-meter mark. Taipei 101 is obviously 101 stories. Obviously the Sears Tower, which is not as tall as Taipei 101, is only 110 stories. Now, there are additional challenges associated with these very tall buildings. Obviously, egress is one of them. It's a long way up and it's a long way down. Stack effect becomes very relevant, becomes a large factor. We know that typically elevators will only go to 600 meters. You can't get ones that do much more. I'm sure that will change in the future. We also have to consider the effects of 9/11 on our designs. And one of the things I'll talk about later is the importance of communication in an emergency situation and how we handle annunciation of a fire. Now, with stack effect, we have to consider how do we keep the staircases clear of smoke. And as also, the stack effect can also produce enormous forces in a tall stack. Here in Dubai, it's a negative stack effect. Elsewhere, it's positive. Now, a lot of people talked about the use of elevators or lifts for evacuation. I'm going to talk about that a little bit later on. Early reliable detection is very important indeed, and there's lots of new technologies out there that aren't being used in buildings now that can be used in the future. that give us not only early reliable detection, but also eliminate the issue of false alarms. And I'm also going to talk about the British firefighting shaft, because I think that is a good invention by the British. Now, nuisance fires. Now, this is a term that I think not many people outside the fire industry will recognize. You will get fires in a building, but those fires do not necessarily result in death or serious injury. And there are statistics around that enable you to calculate how many fires you might get in your building. And many years ago, I worked on the Twin Towers and worked with the Port Authority there. And we did some quick calculations and calculated that you're going to get 3 or 4 fires a year in those Twin Towers and the associated low-rise buildings. And that was about right. They got 3 to 4 fires each year. Most of those went unreported because they weren't severe. Nothing happened. 1 or 2 sprinklers went off and the fire went out. No big deal. And the office space was up and running the very next morning. We did a project in Qatar, the Qatar Financial Centre. That's a 32-storey building, quite low. In fact, very low compared to a lot of these buildings. We did a fire drill there. We evacuated the building and monitored how successful that evacuation was. And I was surprised to find out how difficult people found it to get down 32 flights of stairs. Bruce is there nodding in the audience there. It was actually quite a significant issue. So are stairs safe? I've got some figures here that's quite interesting. 19% of people have some form of disability that will prevent them from using staircases. Now, we know that there's probably 2% of the population are wheelchair users. Clearly, they can't use staircases. But there's issues of tiredness, becoming dizzy, slipping down staircases. And I think I heard some figures earlier on, but the figures I have is that a very fit person can probably do 40 stories in about 12 minutes. That's on an empty staircase. Now, statistics from the UK for a 5-year period between 1994 and 1999 show that there were over 8,000 injuries occurring in staircases. 5 of those were due to fire. Now, these weren't fire evacuations. These were simply people in buildings going up and down staircases in their day-to-day business. And out of those, that 5-year period, there were 13 fatalities. So really, staircases aren't a very safe way to move around a building. You can hurt yourself and kill yourself. So why not use lifts? What's stopping us doing that? Obviously, years of training. The sign on the right there shows that we clearly can't, we're not supposed to use the lifts. We have to use the staircases. Hollywood's a big factor there. I'm sure you've seen Jedi Knights escaping through lift shafts and all sorts of films, James Bond and so on, Tower Inferno. These people always get stuck in lifts. I've seen movies where the lift fills up with water and people are trapped in the lift and so on. So there's a lot of Hollywood out there. And there's no procedures in place so far. I know that NFPA are writing some procedures now. So the big issue about waiting for a lift in a fire is that you've got to get out of that space very quickly. You can't hang around waiting for a lift. You've got to get off that floor quickly, and that's usually by a staircase. And the other issue that's happened in the past is that there have been instances where the elevator gets recalled to the fire floor. Obviously, that's a very bad thing, and there were some issues where heat-sensitive lift calls were set off by the fire and caused the lift to go to the fire floor itself. So we need to consider protection from, obviously, smoke, fire, and water, and make sure that there is a very reliable electrical supply to those elevators. Now, what I would call normal high-rises in terms of how the current codes look at it is, say, maybe less than 100 meters. There's a lot of buildings around there at that sort of height. My own view is that the UK codes have very limited experience in high-rise. I mean, you've heard already in the earlier session that it's possible to have a high-rise building that has a single stair and, until recently, no sprinklers. So you could have a super high-rise single stair building which is unsprinkled. And I think we probably all agree that that's not acceptable. I think the US codes are much better. There's been some recent changes in the IBC, which I'll touch upon in a minute, and also the NFPA now, which is widely accepted here, will be coming up with some new guidance. I know what code writing is very hard. I've done it myself. I've written some British standards in the past when I used to work in the UK, and it's very difficult to come up with some ideas of how to design a building in a vacuum. It's actually quite easy to come up with a solution when you have some drawings in front of you. It's just that vacuum that is difficult. So very briefly, some of the additional requirements under NFPA for very tall buildings is to make them wider, go up to 1420 millimeters, that's 56 inches. You need to make these stairs wider once it gets to 2,000 people. 2,000 is a reasonable limit. And I think also there's, once you get to 1450, you can have counterflow in the staircase, so people coming up can pass people coming down the staircase. The IBC, section 3008, is entitled Occupant Evacuation Elevators, and this is actually a very good attempt by the IBC to come up with a series of codified measures to allow the safe use of elevators for egress. It talks about egress capacity. If you have elevators, can you reduce the number of stairs? The size of refuge areas, whether it's 0.3 or 0.5 square meters per person, power supply criteria, and all sorts of different criteria that regard the protection of the enclosure. And that was due to hit us in 2008. But unfortunately, all those were rejected. So it looks like we're going to be back to square one with no guidance from the codes. Now, this is a typical British standard firefighting shaft. It basically shows a lobby, a staircase, and a firefighting lift with an access door. It's absolutely essential for a rapid attack of the fire. It makes it so easy for the fire brigades in the UK to access buildings, which is probably a good thing because they're probably single-stair, non-sprinkled buildings anyway. The protection of all the water and the communication is actually within the shaft itself, and that's a 2-hour fire-rated shaft. It's smoke-proof, so it's allowed to be ventilated or pressurized or whatever you want to do. In this particular case, there's simple openable windows. And the riser outlet standpipe is actually inside the lobby. Here's some other configurations that might be useful for taller buildings. So the one on the left there is in a lift bank, and you could enclose the rest of that lift bank to make those all firefighting standard. So smoke control to these firefighting shafts, you can model these. You can use CFD to work out what the stack effect's going to be, whether or not the shafts and the elevators and staircases and lobbies will be tenable. And if you do some very quick hand calculations, you can work out that in these very tall buildings, say 150 stories or more, you could get pressures of plus or minus 300 pascals. Now that will easily close doors and prevent them from being used. So there's some significant forces that you can get in these stair shafts and elevator shafts. So the use of lifts and elevators. As I mentioned before, it's essential for emergency services to access the building. It's very useful. The occupants are likely to use lifts anyway in a fire event, especially if you're in one of these buildings where you're using the elevators every day. Some old data that I had from when I was involved in writing some guidance in the UK, we had some data that suggests that using elevators for evacuation will reduce the evacuation time by 50% at least. As you've heard before, we're looking now, if you have a fully designed system, you can evacuate any building within 1 hour. That's if it's designed for elevator evacuation. So performance design approach is obviously based on research, based on engineering analysis, and I think importantly, each design that we've looked at of super tall buildings is very, very different. People don't build these landmark buildings to look the same. So it's very difficult to come up with rules and regulations for these very tall buildings because they are fundamentally very different. So once we've got our robust shaft construction and our reliable power supply, and we've considered the major risk of waiting for the lift and providing some sort of smoke-protected lobby or waiting area, or even the designs are so different, there's so many different ways around that issue. And the important thing is to come up with a controlled lift operation as well. There are software packages out there that we can use to speed up evacuation of a tall tower. I mentioned before how important communications was for the evacuation of a tall tower, and we think it's essential that these warnings aren't simply bells or sirens or recorded messages that go off when there's a fire, but they are live warning systems. They must be remotely controlled from a safe place, preferably not inside the tower that's at risk. And if you've got apartment buildings, you could have these annunciations within the apartment themselves. You have LCD screens, you could have people's TVs, you could have all sorts of systems these days that can give you warning of what to do in case of a fire. And again, you can actually now put these systems within the staircases themselves. And I don't mean just a simple sign saying fire exits down that way, but live interactive panels. You can have those in the elevators, and you can also have those in the lobbies or the refuge areas or whatever it is you are considering for your particular design. Now this shows the concept of an egress model. We use these to estimate how quickly we can evacuate a building and run these models over and over again, because each time you run them you'll get a slightly different answer because they are risk-based. So we can put in various types of occupancy, so whether it's a retail mall or an apartment building or an office block. And then we can combine those into a much more elaborate model. Now this is probably a bit difficult to understand because it is actually a working tool. You can see the green lines with people spiraling down, and those are actually staircases. So this particular building has 4 staircases shown. And you can see the elevators rising and falling and going back up to collect more people. And you can see little people running around at the bottom there. This is speeded up. This is very much in fast forward mode. And this gives us a good idea of where our bottlenecks will be and how long it will be to evacuate the entire building. And we can play around with where the fire scenarios, where the fire locations will be, and so on. With modern computers now, these models aren't too difficult to run. They are very large files, but again, today we have the capacity to run these models quite efficiently. So in conclusion, my view is that we need to use performance-based designs over the standard building codes. And a great example is 3 staircases as required by the IBC code. Is that really a requirement? Can we have 2, or maybe we need more? And this width of 1400, maybe that is reasonable, but in some designs that may be completely unreasonable because each design is vastly different. And if we do have elevators for escape, we should be able to get some reduction elsewhere in the building design. Now, whether that's in the number of staircases or the width of staircases, that's a matter for us to decide. I mentioned that live communications is key. But again, my point I want to make here is that because each building is very, very different, and I've never seen two super high rises look the same. I think it's up to us as the fire protection engineers to decide how we design these buildings rather than resort back to some code that's in a way written in a vacuum. Thank you very much.